All right, let's jump straight into this explainer. Today, we're going to frame the complex physical chemistry of solutions as a highly practical, real-world case study in molecular engineering. You might think of chemistry as just, well, mixing random liquids in beakers, but it's actually about architecting interactions at the microscopic level to achieve very specific macroscopic results. It's a true blueprint.
So here is the roadmap for our step-by-step guide today. We'll cover the anatomy of a mixture, the concentration decision tree, phase changes in vapor, the intermolecular diagnostic matrix, the power of quantity, and we'll wrap it all up with the master implementation blueprint.
Okay, step 1, anatomy of a mixture, understanding the 9 types of solutions.
When we talk about mixing solutions, our primary focus is usually on liquid mixtures. Think of something like glucose and water. The absolutely crucial rule here is like dissolves like, meaning polar solutes strictly require polar solvents because their intermolecular forces just have to match up. But the biggest takeaway for your foundational understanding is this: the solvent ultimately dictates the physical state of the entire solution. It's the boss. It's the dominant component that sets the stage for the whole shebang.
Moving on to step 2, the concentration decision tree, choosing the right metric. Now, before you start calculating anything, as an engineer or a chemist, you literally must ask yourself this one pivotal question. Does your system experience temperature changes? Because if it does, it causes a fundamental divergence in how you have to formulate your chemical solution.
Think about it. We all know that heat expands volume, right? So if you're using a volume-based metric, like molarity, in an environment where temperatures are fluctuating all over the place, your concentration values are going to physically change as that liquid expands. This forces chemists to pivot and choose temperature-independent metrics like molality, especially when dealing with super precise, sensitive measurements like colligative properties. This ensures the mass remains strictly constant, completely regardless of the heat. And this isn't just academic. You can clearly see right here why different industries rely on highly specific concentration metrics. Sure, your standard lab reactions might just use molarity, but pharmacy and medicine, they rely heavily on mass by volume to perfectly and safely dose intravenous saline. Meanwhile, massive factories pumping out industrial bleach rely on mass percentage, or W by W. Why? So their product maintains a completely consistent potency, even if it's sitting on a sweltering hot factory floor.
Let's step into section 3, phase changes and vapor, forcing and trapping molecules.
To really wrap our heads around Henry's law, imagine a gas piston. To dissolve a gas, you have to apply external pressure to physically force it into the liquid. But this creates a fascinating temperature paradox. Because dissolving a gas is actually an exothermic process, meaning it inherently releases heat, raising the environmental temperature fights directly against the process. Thanks to Le Chatelier's principle, as external temperature rises, gas solubility totally drops. It is exactly why your warm soda goes completely flat. Before we go any further, we need to quickly lock down what a non-volatile solute is. Simply put, it's a substance that does not readily evaporate into a gas under existing conditions. Just think of everyday stuff like table salt or sugar. We need this definition because it unlocks one of the most powerful control mechanisms in all of physical chemistry. Adding these solutes creates what we call the solute blockade. In a pure solvent, molecules evaporate super easily. But the second we add a non-volatile solute, those new particles physically take up surface area. They act as literal roadblocks that trap solvent molecules down in the liquid phase, forcefully lowering the overall vapor pressure. And Raoult's law proves that this lowering depends strictly on the mole fraction of the solute doing the blocking. All right, step 4, the intermolecular diagnostic matrix, predicting solution behavior. We can quickly diagnose core solution behaviors by comparing their deviations. Take the positive deviation, what I like to call the hate mixture. Here, the A-B forces are weak, energy gets absorbed, the whole volume expands, and molecules escape really easily. Think ethanol and acetone. Now contrast that with the negative deviation, the love mixture. Here, substances like phenol and aniline form much stronger bonds together than they ever did apart. The reaction releases heat, it contracts in volume, and it firmly traps the molecules together. But here's the catch. These extreme deviations lead directly into the azeotrope trap. This is a massively frustrating reality for chemists where a binary mixture boils at a constant temperature. Because the liquid and vapor compositions become perfectly identical, standard fractional distillation completely fails. You literally can no longer boil them apart. Minimum boiling azeotropes pop up from large positive deviations, while maximum boiling azeotropes come from large negative deviations.
Let's shift gears for step 5, the power of quantity, colligative properties. At the very center of our blueprint are the 4 colligative properties. Now, these properties are totally unique because they depend exclusively on the sheer number of solute particles relative to the total particles in the system. The physical properties of your solution will shift exactly the same whether you're dissolving sugar, salt, or urea, as long as the particle count is identical. Because this behavior is so incredibly predictable, the primary real-world application is using these properties to determine the precise molar mass of totally unknown solutes. The sheer quantity forcefully shifts the phase boundaries outward. It elevates the boiling point and depresses the freezing point, basically forcing the liquid to remain a liquid over a much wider temperature range. And simultaneously, this exact same particle count drives the molecular tug-of-war we see in osmotic pressure. This invisible pressure is exactly what dictates whether your red blood cells remain healthy and isotonic, or if they catastrophically shrink or burst. Finally, step 6, the master blueprint, putting it all together. By following a systematic 3-step approach, you can successfully engineer and predict the physical boundaries of pretty much any chemical system. Step 1, identify the solvent. Step 2, determine the intermolecular forces. And step 3, carefully quantify your solute. Ultimately, mapping out molecular identity versus quantity is the whole game. While the specific identity of the molecules dictates how a solution is formed and whether it behaves ideally or not, it's the sheer quantity of those dissolved particles that really turns the gears and drives the macroscopic physical engine of the entire system. However, as with any kind of engineering, you always have to account for reality, and that is exactly where the Van't Hoff factor comes in. It's an absolutely essential mathematical correction for when molecules unexpectedly break apart, like salt dissociating into multiple ions, or when they associate and clump together into dimers in the real world. If you only calculate your expected particles without actually observing the real-world particles, your blueprint is going to fail. So, I want to leave you with one final provocative thought to ponder as you look at the complex mixtures that make up the world you interact with every single day. If reality routinely breaks the rules of expected particles, what other invisible molecular interactions are secretly governing the physical world around you? Next time you add a pinch of salt to a boiling pot of water, you're going to know exactly what's happening beneath the surface. Thanks so much for joining me on this explainer, and keep observing the blueprint around you.